In this video, I'm going to continue my series on the parent functions, or the very basic functions that we want to be really familiar with before we go ahead and proceed to function transformations. Okay, so in the previous videos, I've included several parent functions in one video. In this one, I'm actually going to include just an explanation of one, and the reason why is because I find that, I teach high school. But when I show this to high school kids, and I can't blame them because it was kind of weird looking the first time I saw it, but when I show this to high school kids, it kind of trips them up. So I really want to take the time to dedicate an entire video to this. But we're going to call this function the step function, okay, or stair step function, or the greatest integer function, okay. And this is kind of, actually when I learned it, we called it the postal scale function. But it's got its applications and its unique properties, and I just want to discuss those today. So let's go ahead and start with a notation, okay. We're not going to start with the graph this time. We're going to talk about notation. We say, okay, so our function, we'll call it f of x, of course. We say f of x. I'm going to draw in this double bracket here, and they kind of meet a little bit here, but double bracket around our x. F of x is equal to this, okay? And the way we want to read this is, we say f of x is equal to our function value at this x value is equal to the greatest integer. Okay, we'll talk about integers here very briefly, but the greatest integer less than, this is important, or equal to x. Groovy, okay? So this is kind of how we read this function. If you see this, you say, well, f of x is equal to double bracket thing x. You could say that, but nobody's going to understand you. So if we said f of x is equal to the greatest integer that is less than or equal to x, everybody will understand you, at least after we kind of explore it. So hey, real quick, recall that an integer is on the number line here. We say, proceeds left and right. We say 0, 1, 2, 3, 1, 2, 3, negative 1, negative 2, negative 3. The fact of the matter is this. We say the integers are these, like, whole, you know what, I'm going to get flack for this, I know, but these whole number values. And I know that there's probably other math teachers that maybe watch this and say, well, the whole numbers go from 0 on up and are whole numbers. But I just, for the sake of convenience of explaining this, we say, in other words, all these notch marks on the number line, every one of these, okay, is the set of integers. So we just basically could almost look at it this way, just no decimal, okay? So that kind of quick review of an integer is going to help us when we come over here and we draw a fun table of this. Yes, okay. Let's go ahead and take a look at a few values here. And I'm actually going to write this over here. We say y or f of x, but this would be a nice thing to write. We say, okay, so the greatest integer less than or equal to x. What we should be saying. Let's plug some interesting ones in here. We'll go with negative 2, negative 1, negative a half. How about a half? How about 0.75? How about 1? We'll plug in a lot. 1.2, 1.6. Okay, so taking a look at this, sorry, let me scroll back down here. I'm going to plug a few of these in, and for the first few I'm going to use notation, but we say, okay, so negative 2, if we were to plug this in, we'd say f of negative 2 would be equal to this double bracket negative 2, which really means the greatest integer less than or equal to negative 2. And why don't we bring our eyes back over here to the number line? So we say x negative 2 right here. What we want to know is, what is the greatest kind of whole number or integer value that is less than negative 2 or equal to negative 2? And of course, since negative 2 is itself an integer value, it is the greatest integer, okay, or the greatest whole number that is less than or equal to itself, okay. We're just going to go back over here. We say it's negative 2. Okay, the same sort of argument here follows for our negative 1. We say, if we were to plug negative 1 into this, okay, we'd have a negative 1 here instead of a 2, and we say, what's the greatest kind of whole number that's less than or equal to negative 1? And it's simply negative 1. Okay, so we're generating some solution pairs here. Now we'll get to a decimal value, and this happens, this function's everywhere continuous. We will discuss domain here, but we say, okay, so negative a half. What if, let's go back over the number line here. What if we were to plug in negative a half, which actually falls right there on the number line? If we said, okay, so negative a half is kind of like right here, we say, what's the greatest integer value? So the biggest whole number value that is also less than or equal to negative a half. And so we say, okay, so what are the integer values that are less than or equal to negative a half? Well, negative 1, negative 2, negative 3, negative 4, so on and so forth, they're all less than or equal to negative a half. But the greatest one of those happens to be negative 1. Okay, so you notice we got negative 1 here twice. Okay, and we're going to keep running with this, and you'll see a pattern. But we say, okay, so what if we chose a half? Okay, what's the biggest whole number value that's less than this? And there are lots of whole number values less than this, integer values less than this, but the biggest one is 0. Okay. So the way you can kind of look at this is we say, okay, so 0.75 would be right here. It's always just kind of falling back to the last integer value right before it. So we say 0.75, the last whole number value before it was 0. 1, the last integer value that is less than or equal to 1, well, less than or equal to 1, it is itself an integer. We say that would be exactly at 1. We say 1.2, what's the greatest whole number value that's less than or equal to this? We say, well, less than 1.2, the biggest whole number would be 1. Same thing for 1.6. Okay, so let's go ahead and take a look at the graph of this bad boy. We say, okay, so here's our y-axis, our x-axis, and we'll go out a few to the right here, and maybe a couple to the left. Well, we might as well just supplement the whole line there. Okay, so I'm going to switch over to red here. Now we see a little bit better. And they say red is the color of power. But anyways, let's go ahead and graph a few of these points. We said -2, -2. We said -2, -2 is on the graph. So that's left 2, down 2. We'll drop in a dot right there. -1, -1. That is right there. You might be saying, oh, this is going to be a line. Well, check this out. And -1/2, that is, we'll go back a half. We actually have to go down to -1. So we're at the same height we were at when we plugged in an x value of -1. Okay, so we say, how about a half? Well, when we were at a half, we obtained a y value of 0, so it's here. Okay, when we were at 0.75, it was a height of 0. Kind of hard to see there. At 1, we were at 1. Okay, big solid dot. We'll talk about that y there in a minute. At 1.2, x value of 1.2, we were up at a height of +1. And an x value of 1.6, we go up to a height of 1. Okay. Now, if I were to draw in a lot more dots here, you'd notice why we're calling this the stair-step function. But the fact here is this. I'm going to draw in a few intervals of this here. It actually looks like how I'm drawing this. And you're not crazy here. You actually do see some open dots on this graph. Okay? And we'll talk about why that happens. But this is our basic stair-step function, and this is why we call it a stair-step function. It looks like a set of stairs. So now the question has to be this. Okay, so how this necessarily works is, you know, honestly, if all we're answering is the question, what's the biggest kind of integer value that, or the greatest integer value that's less than or equal to me, there's no x value that we couldn't plug in. So you're going to notice here, if we drew in this whole function right here, we drew in the whole darn thing from left to right, we would never have an x value that gave us a y value that's undefined. Oh, excuse me. That one goes there. We don't want that one. And this one goes here, just for continuance. But the domain of this would be all real numbers. So in terms of the x-axis interval for which our function is defined, we say it's defined for all x values from -infinity out to +infinity. Okay? The range is slightly different. The range actually we call the set of integers. And I'm not going to go there on this one, but I do want to explain why the graph looks like it does. So let's kind of focus on maybe right in this area right here. We'll consider these x values down here. But we say, okay, so starting right here, we said this would be over 1, 2.5. What if we went to 2.5? Well, the greatest integer value that is less than or equal to 2.5 is going to be 2. But consider any of these 2 point somethings: 2.6, 2.7, 2.8, 2.9, 2.99999999999. The greatest integer value that's going to be less than or equal to that is going to be 2. So we'd have a height of 2. But the question is, why did we put an open dot right there? Well, think about 3. The moment you plug in 3, okay, we say, what is the greatest integer value less than or equal to 3? Well, that's going to be up here at actually at a height of 3. So what are we going to put here, back down here, when we were, considering this open dot? We have to put an open dot there to represent the fact that this function at this point right here is going to stay at a height of 2, up to, but not including 3 itself. Because the moment we get to 3, we're going to be up at a height of 3. So it's kind of like, for whatever this x value is right here, we say, okay, so how about right here? -3, okay? It's going to stay at a height of -3. It's going to stay at a height of -3 all the way up to the fact where we get to -2. At that instant, it pops up to a height of -2. So we say it approaches this y value down here when it was, say, -2.8, -2.6. It was stayed at a height of -3 and approached this y value right here, but never quite reached it. Okay, so this is our stair-step function. Okay, and it's just important to note that it's everywhere defined. Its domain is all real numbers. Okay, And it has an intercept here at 0, 0. So along with all the other parent functions we discussed, it has an x-intercept at 0 and a y-intercept at 0. Okay, and it just, I guess, jumps vertically at every integer value. So there's the stair-step function, or the greatest integer